This video covers data structures and algorithms, a core course in programming. We'll explore fundamental data structures and the algorithms that use them. Our class overview will introduce you to basic data structures. You'll learn to understand them, analyze their algorithms, and know when to apply them in practice. The goal is for you to understand the tools for storing and processing data, and which tools are appropriate for different needs. This will help you make good design choices as a developer or project manager. What is a data structure? It's about organizing program data for the problem being solved. An abstract data type, or ADT, defines a data object and operations to manipulate it, like insert and delete for a list. Why are data structures important? Program design heavily depends on how data is structured. This impacts the ease and speed of operations, memory usage, and even debugging. Let's define some key terms. An abstract data type, or ADT, is a mathematical description of an object and its operations. An algorithm is a high-level, language-independent, step-by-step process. Algorithm analysis is crucial. We analyze correctness to ensure the algorithm does what it's intended. Performance analysis focuses on running time and storage consumption. This helps us choose the best algorithm for a task. Here's an iterative algorithm to sum the first num integers in an array V. The pseudocode shows initializing a temporary sum, then looping through the array to add each element. We can also use recursion to find the sum. This recursive function checks if num is 0, returning 0 if true. Otherwise, it returns the last element, plus the sum of the remaining elements. This section covers elementary data organizations, including data, entity, and information. We'll explore primitive and non-primitive data types, data structure definitions, classifications, and operations. Data represents values assigned to entities, with data items being single or grouped values. An entity has properties that take values. Processed data becomes information, used for action. Primitive data types are directly supported by the machine, allowing direct operations. Examples include integer, float, double, character, and Boolean. Non-primitive data types do not allow direct operations on data items. These include arrays, structures, unions, and classes. Data structures are classified as linear or nonlinear. Linear structures arrange data sequentially, like stacks, queues, and lists. Non-linear structures represent elements hierarchically, such as trees and graphs. Common data structure operations involve processing data. These include traversing each item, searching for specific values, inserting new data, deleting items, sorting, and merging two similar sets. What is a list? It's an ordered sequence of elements, all of the same type. Common list operations include insert, find, delete, checking if it's empty or the last element, and navigating through elements. Lists are used in many ways. Simple examples include representing polynomials, handling unbounded integers with many digits, and storing text strings. There are two main ways to implement lists: array-based and pointer-based implementations. Each has its own characteristics and use cases. Let's recap arrays and pointers. These are fundamental concepts for understanding how data can be organized and accessed in memory. For array-based list implementation, the basic idea is to pre-allocate a large array. We track the current size with a count variable and shift elements when inserting or deleting. This slide visually depicts the array implementation of a list, illustrating how elements are stored sequentially within a pre-allocated array. Module 1 covers algorithm analysis, asymptotic notations, and the time-space trade-off. We'll also delve into searching techniques like linear and binary search, and analyze their complexity. For reference, we recommend Data Structures and Algorithms with Object-Oriented Design Patterns in Java by Bruno R. Priess, specifically the chapters on algorithm analysis and asymptotic notation. What is an algorithm, and why analyze it? An algorithm is a step-by-step procedure to achieve an end. We analyze its running time, memory, code size, correctness, complexity, and robustness. The basic axioms define constant times for memory operations like fetching and storing operands, elementary arithmetic, and method calls or returns. For example, y equals y plus 1 involves two fetches, one operator, and one store. Here's a C-like function to compute the summation of n natural numbers. It initializes a result to 0, then iterates from 0 to n1, adding 1 to the result in each step. This section introduces analyzing recursive methods. We'll specifically look at the factorial of a number n, which can be defined iteratively or recursively. For recursive factorial analysis, the function checks if n is 0, returning 1. Otherwise, it returns n multiplied by the factorial of n1. Analyzing its running time, t of n, requires understanding its recursive nature. Summing the columns results in a recurrence relation where the function is defined in terms of itself recursively. This equation describes the running time. We can solve recurrence relations using repeated substitution. The idea is to substitute the definition of t of n1 into the equation for t of n, repeating the process to simplify it. As an exercise, analyze the time complexity of the iterative method for calculating factorial using pseudocode. This will reinforce your understanding of algorithm analysis. Another example is finding the largest element in an array. This function initializes result with the first element and iterates to compare and update result if a larger element is found. The running time of this program, t, depends not only on the number of elements n, but also on the actual array values. Summing the entries from the analysis table reveals this dependence. Average running times consider the probability of certain conditions. We can express the sum of running times by incorporating the probability that a true statement line is executed. By substituting the expression for pi, we can further refine the calculation of the average running time, taking into account the likelihood of each element being the maximum. Replacing the value helps simplify the equation, allowing for a more concrete calculation of the average running time for the algorithm. We also analyze best case and worst case running times. The worst case occurs when a specific line is executed in every loop iteration, while the best case is when it's never executed. This slide provides a summary of the key concepts covered in the video up to this point, including data structures, algorithms, and their analysis. Asymptotic notation helps us compare algorithms. If we have two algorithms, A and B, with running times tan and tbn respectively, we might think comparing them is simple. But is it? Often, tan0 might be less than tbn0 for a specific input n0, but this isn't true for all n. We typically analyze the asymptotic behavior for very large problem sizes to understand which algorithm performs better in the long run. Asymptotic analysis defines the mathematical boundaries of an algorithm's runtime performance. It allows us to determine the best, average, and worst case scenarios. Commonly used asymptotic notations include O, big O for upper bounds, omega, big omega for lower bounds, and theta, big theta for both upper and lower bounds of an algorithm's running time. Big O notation, invented by P. Bachman in 1892, formally expresses the upper bound of an algorithm's running time. It describes how the function grows. This slide outlines the properties of big O notation, which are essential for understanding and applying it correctly in algorithm analysis. Certain big O expressions occur frequently and have specific names. This table lists some of these common expressions and their usual nomenclature.